Okay, I will get started. I'm here today to talk to you about ways of optimizing content delivery networks. And I know this is a somewhat unusual topic for a storage conference, but there's an awful lot of storage involved in content delivery networks. I'm Andy Banta. I've been doing storage development for about 30 years now. Ironically enough, this is only the second time I've attended the Storage Developer Conference, so I have a lot of time to make up for. I want to start off by just giving a couple quick comments on engineering. So every discipline of engineering that's out there uses simulations to improve their products. This includes electrical engineering, chemical engineering, mechanical engineering, civil engineering, bioengineering. All of these different things run extensive computer simulations before they even attempt to do their first experiment. They do it because it's cheaper, faster, and more flexible than actually trying to build things out and test them that way. Isn't it about time that we start doing the same thing with software development and system design? I was talking to another company last week who were trying to do some testing on some GPUs, and they said they were running some models on the GPUs that they had, and the models were at most using the GPUs about 35% of their capacity. So they looked at it and they broke it down, pulled the algorithm out of the AI that they were using, and tried running that directly against the GPUs. And that was only using GPUs 60 to 65% of the time. So even the best software that's out there today is not making full use of the hardware that's available. And this is something that you would be able to figure out if you simulated that software and ran it against models and said, oh, hey, we're not actually making use of all the silicon that's out there. That's one of the things that Magnition is interested in doing. So what we do is build large-scale, complex simulations of various different software and systems that you can run against real-time workloads. We do this by allowing you to build out the various different components, put them into a framework that Magnition has built, and have these different components interact with each other and run real-time workloads against this. You can use either traces that exist, or you can run synthetic workloads, or in best case, you can actually run a genuine application against this simulation framework to find out what the results are going to be. We also allow you to have a set of constrained variables that you can change along the way to find out what's going to improve the simulation. And while it's constrained, you still end up with the ability to run tens of thousands or hundreds of thousands of different variants on the simulation to find out what's going to make the best performance for you. I'm going to start off by talking about caching, simply because the piece of content delivery networks that's the hardest to get right is the cache. And there's a handful of different caching technologies out there. The most common ones are, a hit or miss, where either you find something in the cache or you don't. There's also the idea of tiering, where you have a promotion and demotion between the various different levels. And when you get into multiple levels of tiering, like 3 or 4 levels of tiering, it becomes an impossible task to actually optimize this appropriately without running simulations with real-time workloads against it. So I'm going to specifically talk about the hit or miss cache. This is one of the most common ones. It's typically used to to say, a typical hit or miss cache would be something that has a bunch of commonly used items stored in it, and if you look something up, if it's in the cache, it will return it quickly, and if not, it needs to go off and find it from the origin somewhere. The nice thing about these is they can actually be tuned quite a bit. They're not, well, I'm sure an awful lot of people just think of a cache as a very, very simple mechanism. There's actually an awful lot of tuning that you can use. So the way that we model these caches is we simply say that we have a cache, and there's an input that comes into it, and there's a fairly high-speed media that's attached to it, and that's what happens when you get a hit. So it will return the result or store the result in the high-speed media. In the case of a miss, it will go off to what's considered the origin. So it's a lower speed media or something that's farther away, typically in the case of a content delivery network, something that's much farther away. And for content delivery networks, these are typically multi-tier caches. So they would, lots of times there would be like a DRAM component of the cache and an SSD component of the cache. And there might even be more tiers than that, but just for a simple case, we'll go for 2 tiers here. And as I said, if you dig down into the cache, you end up with typically very separate algorithms for allocation of that in that cache, lookup in that cache, and eviction in that cache. And so with that, I wanted to bring up some work that was done by an intern at our company this summer, who came up with a new, very simple, very efficient eviction algorithm. So the whole idea here is that lots of times eviction algorithms do all sorts of predictive analysis or come up with all sorts of different algorithms. The most common ones, the most common simple ones would be like least recently used, where you look for the thing that has most recently been referenced in a cache and throw that out when you need to evict something. Another method would be FIFO, so the first thing that goes into the cache would be the first thing that goes out. This isn't very efficient if you have something that gets referenced quite a bit. The algorithm that she came up with, she named Civ, and it's a very simple approach. It uses a singly linked list for eviction, and there's a pointer that starts at the tail of the singly linked list, and anytime that it finds an item that was in the list, it will say, if you were referenced previously, I'm now marking you as unreferenced. And when a cache hit happens, when something wants to get inserted into the cache and it's already in the cache, that entry gets marked as referenced. So as the pointer moves forward, it unreferences things, and when an item is found in the cache, it's marked as reference. So we know that that's an item that will be used or has been used since the last time the pointer moved by it. On a cache miss, the pointer will move to the next unreferenced item in the list and delete it and insert the new item at the head of the queue. So as it moves forward, so it's the newest thing in the queue is always the head of the queue. And very simply, when you, sorry, it skipped over there. When you reach the head of the queue, the pointer simply moves back to the tail and repeats the process over and over as it's going by. So this is, hopefully the graphic helps explain it a little bit. The orange means that something has been referenced. The gray means that something is unreferenced. And this is an incredibly simple, incredibly efficient algorithm. You don't actually need to move data around like you typically would in an LRU cache, where you would need to rearrange the pointers to end up with getting something done. And it's going to age things much more appropriately than a FIFO, which is going to kick out the first thing that was ever put into it, which might be something that gets referenced fairly frequently. So in some testing, this actually ended up with lower miss ratios than on a handful of applications that it was tried in. So it was used to replace either a FIFO or an LRU in a handful of the applications that were listed. I can't tell you what all these applications do, but they're apparently fairly common things that are out there that would use a cache. And you can see this is the reduction in miss ratios that we see. And additionally, she tried it out and said, hey, what if we actually use this eviction algorithm instead of LRU or instead of FIFO in some of the more complex eviction algorithms, some of the ones that do much more computation but still have to have some way of deciding what way to get rid of it. And you can see that in those cases where it's just the straight eviction algorithm used all by itself without doing anything else, this is the type of miss ratio that it provides. And if you replace the LRU or FIFO in one of these other cache algorithms, you can see that in just about every case it outperforms the algorithm that was in there. It's like only the last one does it not outperform that algorithm. It's also incredibly compact. So This was added to a handful of existing libraries that are out there, and you can see in every case, it ended up being less than 20 lines of additional code in it. And if you go to the resources I point you at on the next page, you can see that the entire algorithm itself, including the ability to print what's in the cache, is 71 lines of Python. And here are the resources for it. And the research wouldn't have been complete without coming up with the shortcomings of it. And the shortcomings are that it's not necessarily something you would use for something like a storage cache, because if you scan the entire contents, you're going to end up referencing everything, and you're going to end up with thrashing the cache. So it's not what's she labeled it as not scan resistant. So let's go on and tackle the larger problem of optimizing content delivery networks at scale. So we're all storage people here, so I'm going to give a little bit of a primer on what content delivery networks are. The whole idea is that you have a web server of some sort that has some sort of content in it, and people from all over the earth are going to be attempting to get to content on it. And this doesn't scale very well. The whole idea is that if you have 1 million people all trying to hit one server farm of web pages, you end up with a throughput bottleneck getting there, and you end up with capacity ability on that server to service all those requests. And I mean, we're talking about things like movies or picture servers or news servers. These are all the various different things that you would potentially have. And I'm sorry, it's advancing too quickly. So the whole idea with a content delivery network is that you put together a global network that can handle the requests that come in and hopefully only feed requests to the main content server if it's not found somewhere in the network. And here you can see the connections being made to the network. One of the first companies to do this back in the 90s was Akamai Technologies, and they're still one of the biggest players in the content delivery network. But since then, an awful lot of other players have come in to the fray as well, who are doing all sorts of interesting things. Some like the big cloud providers that are out there, and some that are specifically in the business of doing content delivery. So the way this works is it's not just a network, it's not just like something you connect to. This global network is full of points of presence, or POPs, as they're typically called, and then you have these POPs spread all over the world. And these POPs will attempt to satisfy the content request that comes in from the individual user and deliver it to them. And if it can't, it needs to go back to the main web server to deliver that content. So let's drill down a little bit on what would be inside the POP. Typically, you'll have some sort of load balancer out front, in front of it, that figures out how to spread load among all the various different servers that would be in a POP. And the POPs that are out there could be anywhere from just a couple servers to, in some case, hundreds of servers, depending on what your content delivery network is and who's providing it. Sorry, PowerPoint doesn't advance as quickly as I want to now. And typically these servers have, in the example that we're going to be talking about here, the servers are going to have a layer of DRAM in it and a layer of SSD. So let's blow this up a little bit more so we can concentrate on some of the things that we want to try playing with when we want to optimize our content delivery network. So we can vary the size of the various different components. We can say, well, what if we cut down on the amount of DRAM and increase the amount of SSD? This would probably be a cost-saving move to allow your servers to be less expensive. Or you could flop it around and say, let's increase the amount of DRAM and decrease the amount of SSD. This would be if you need your cache server to be very fast, if you need the results to be very fast coming out of it rather than simply lots of content. Typically, with a content delivery network, speed is one factor, but the ability to have the information that you need stored is a more important factor, because you really don't want to send that user back to the origin, which could be a several-second round trip. I don't know, has anybody tried looking up SDC video from like 2022? It takes YouTube about 20 seconds for it to come up with that content for you, because it's not something that's hit that often. And it has to go back to probably its origin to dig that stuff up. Try it sometime. Usually now everybody's going to try it and it'll all be cached properly. But but if you go look for a video on YouTube that hasn't been used for quite a while, you will see that YouTube has to spend time to go get it from whatever cold storage it's on. Another experiment that we tried is let's just try getting rid of the idea that we have DRAM cache in every server, or we did similar things with let's see if we don't have SSD cache in every server. There are other games that we can play here where it's we can say let's try out the experiment of every SSD being its own secondary cache, and each server has its own secondary cache, versus let's have a distributed secondary cache that's spread across all of the servers in the farm. What are the differences that we would get from that? We can try different load balancers on this. We can say, let's do a pure round robin. Let's do a least full queue. Let's try to do a little bit of intelligence in the load balancer and try to send this request to the appropriate server in the POP that might have already serviced a request similar to this. We can also play around with what is our first level cache and what is our second level cache. So lots of times, the way you typically think of it, especially in a storage world, you would say, well, of course, the first level cache is going to be the fastest cache that's available, and the secondary cache is going to be the next fastest cache that's available. But as I mentioned, with the content delivery network, it's more important that you get a hit than you necessarily deliver it in 1 millisecond versus 10 milliseconds. So if you think about this, if you put the stuff that's more commonly used into RAM, yes, it will get delivered faster, but you can also work with the approach of you can put things into SSD first, and if they're hit more than once, you can push them up to DRAM where they'll get accessed more often. But if the first level cache is not used, you end up not wearing the SSDs quite as much by not thrashing the amount of information that's in them quite as often. And this was entirely done for wear leveling on the content delivery networks that go with this approach. And as I mentioned initially, you can also just play around with the cache algorithms and try different lookup or allocation or eviction algorithms for each one of the caches that's available as well. Pardon me. So let's start talking about some of the experiments that we ran. This was all conceived by the same intern that I was talking to you about. She used this to write her doctoral thesis. And this is pretty much the configuration that she came up with that we wanted to simulate. So the whole idea is that we have a handful of content delivery network traces, and we got these traces, we got genuine traces from both Wikimedia and Cloudflare. So these were not simulated traces. These were actual days worth of HTML requests to these content delivery networks. Cloudflare anonymized theirs, so we couldn't actually tell who was actually making the request. But we were able to run these genuine traces against the simulation. In this case, it would come into a cache engine, and we would be able to have different cache configurations, and we'd be able to have different initial considerations, and we would have various different ways of optimizing this. And the end result would be that we could get a complete spread of graphs of performance results, and we could also get optimal configurations that were found by this. And this is what it looks like inside the Bangdition Designer, where if we look at a graphical representation, each one of the components just ends up being a block with various different lines connecting all the various different blocks. Each component could be modified along the way, and you're able to apply different variables during the various different runs to make this happen. So let's actually run through just a quick view of what a designer might see trying to run one of these simulations. So this is, start to finish. This is jumping into the Magnician Designer, and you go into a repository in your system and find the example that you want to use. And here you have the various different source files associated with it. And you go down and you look into in this case, we're doing the CDN cache example. And here's what the code would look like. And here you get a graphical representation side by side with the code. So if we take a little bit of a look at the code, we have all of our definitions up at the top of the code. And then below you can see the simulations for each one of the components. And lots of times there are not that many lines. They're for each component. Sometimes there's few as like 10, 15 lines, and sometimes they're only about 70 or 80 lines. We blow this up into a graphical representation. This is what a pop would look like. And in this case, we're actually talking about a tiered pop. That's not something that I talked about in the examples, but if you have a pop that has two different types of tiers in it, you would have tiered requests. And here, if we drill down into this a little bit farther, we can see this is what it looks like inside one of the pop tiers, where we have a series of pops, and we have a load balancer that takes care of requests coming into it. And if we drill down into the pop itself, we can see that we have a couple of different caches inside the pop, and the caches are on the right side of this, and we can see an SSD and a DRAM on the left side. And I realize it's very small. And if we open up one of the caches itself, well, this is showing the connections, but we can see that inside that cache we have various different components we have a controller, and then we have the allocator, the lookup algorithm, and the eviction algorithm that go with it as well. So this is how we've separated a content delivery network into various different components, and the way that we simulated these various different components. And this is the piece that the developer would write. The developer would write the code. We use a framework called lingua franca, and it's essentially the code that gets put in there is largely just C code that also has some of the lingua franca primitives in it that show how the connections are made between the various different modules. So for our case studies, as I mentioned, we simulated things from Wikimedia and Cloudflare, and we used the genuine workloads. We did variations along the lines of what I showed you earlier with the various different L1 and L2 sizes, the various different eviction algorithms, the various different DRAM and SSD ratios, and various different load balancer algorithms. So we ran 125,000 different simulations with a day's worth of data in each one of them. So we ran somewhere in the neighborhood of 500 years worth of simulations over the course of several weeks. It's 500 years worth of data run through this thing over the course of several weeks. So the way that we configured this is we had the simulations have a configuration file, and this is really all we needed to change in that configuration file to simulate whether we were attempting to mimic what Wikimedia did or whether we were attempting to mimic what Cloudflare did. The other thing that you see here are there are various different things in here that have variable number of elements in them. So when this happens, it means that we want the simulator to run through each one of these various different variants and try them all together to come up with what the best result would be for each one of these combinations. So if you start multiplying this out, you can see that we're already talking about thousands of different variants that this one simulation would run to find out the best results. So this is just a quick graph of what we did with the Cloudflare, and this is one example of 3 different variants. So this these graphs represent about 37,000 different simulations that were run, and the variant that the piece that we're graphing here is just how large the cache is in comparison to the working set size. And the important thing here is that we can see as we increase the size of the cache, if we make the cache be like 5% of the working set size, we end up with far fewer misses than if we have it just be like 1/10 of 1% of the cache size. But the important thing here is the rough shape of these graphs is about the same, which tells us that the algorithms don't dramatically change based on the size of the cache. They're pretty much operating the same type of thing. Now, I mentioned up here that we're talking about multiple objective optimizations. So in this case, the objectives that we went for were both byte miss ratio, which is roughly a measure of performance, and cost. So those are two of the objectives that we optimized on to come up with the best results. After discussions here, especially last night, over the past few days, one of the easier things that you could optimize on as well is power consumption. That could be one of the things that you could simulate for and figure out what is the optimal power consumption. Because an awful lot of things that we're talking about end up consuming huge amounts of power, and while we don't really care about power in this country, there are other places in the world where they do. And so I did want to mention that if you're looking for various different objectives that you could simulate on and come up with answers for, power would certainly be one of them. And here's another different representation of how we get some of the data, where we color code the values that we get with various different colors and end up with a heat map. And this way, just with a matrix of 100 different values here, you can kind of get an idea of what variables affect things in various different ways without actually needing to go read each one of the numbers and get an idea of what's going on. It gives you a quick idea, just visually, of how this various different algorithm is working in various different ways. I'm just showing you the various different ways that we represent the data. So with this example that we talked about, we ran about 90,000 different examples of the Wikimedia traces and about 40,000 different, 37,000 plus of the Cloudflare. And here, if you take a look at it, the red dot is the baseline. This would be if we use the exact algorithm that Wikimedia or what the Cloudflare used in their content delivery networks. And the big blue block shows all of the various different configurations that we ran against it. And you can see in just about every case that the configurations we had outperformed Wikimedia. I think maybe this means that next time when Wikipedia asks you to donate those $2, do it. It clearly shows that their content delivery network algorithm isn't as good as it could be. And in fact, you can see that even our median example, that's the bar in the middle of the box, is better than their algorithm. By comparison, you can see with Cloudflare actually has a pretty good algorithm. Now, we did come up with configurations that outperformed it. So you can see that there's a handful of area in that block that's beneath the baseline, the red dot baseline. But you can see that even our median example wasn't as good as their baseline. Any questions on this? I mean, you're understanding what you're seeing here? Okay. So I mentioned that this was a multi-objective optimization. So in this case, we are looking at both byte miss ratio, or gross performance, and cost. And we have Wikimedia and Cloudflare again. And the first set of bars are for byte miss ratio, and the dashed lines that go across are the baseline for, that would be the baseline byte miss ratio and the baseline cost for each one of those examples. And you can see with the byte miss ratio, we far exceed what Wikimedia did at a slightly higher cost. We can see that if we go with the absolute minimum cost, we do not get as good as the Wikimedia baseline is. And just to be clear, cost in this case was simply the ratio of DRAM and SSD. So we simply did that. That was the only cost basis comparison that we did. If you get into more pieces of the servers, I'm sure the cost would change as well. But just to come up with a cost basis, it was the amount of SSD and the amount of DRAM were the cost factors. And the specific experiment our intern wanted to do is represented by the last set of bars. It was a very specific set of algorithms, and you can see that, again, it beats the performance, but slightly exceeds the cost for Wikimedia. By comparison, if we look at the Cloudflare, we can see that the optimum beats the performance, but again has a higher cost. The lowest cost, of course, has the worst byte miss ratio. But with her experiment, she got roughly the exact same byte miss ratio with Cloudflare, but at a far lower cost. So this is, we certainly collaborated with Cloudflare to get these traces, and we are certainly going to be feeding this information back to them. And I just wanted to, show you more pretty graphs of all the various different things that we do. This is, I'm not going to go through and explain all of these. I just wanted to show you that we have loads of different ways of representing all the data. And in some of these, it becomes very clear where the curves are, where the horizons are, with the various different data that's available to you. And in some cases, it's not quite as obvious unless somebody draws in the lines for you. But the same, those horizons exist with various different sets of data, even if you can't necessarily pick it up. And so this is what Magnition did to try to figure out how to optimize content delivery networks. And we've been doing this for quite a while. We have ways of doing this on the fly for various different storage configurations, content delivery networks, CXL networks. I don't know if anybody attended my talk on Monday, but we use this exact same framework to do CXL simulations. The framework is the same. All we do is plug in different components and optimize on different things that we're trying to do. And if you go back and look at that talk largely talks about how you can test drive CXL components before you can buy them. There aren't that many CXL components that are on the market, but if you want to test out how they're going to work in your environment, you can simulate them and run them against your genuine applications. More than anything, what Magnition does is generate research papers on this type of thing, and we have a handful of awards on this as well. At the same time, we have worked with a very large storage company who happens to be represented here but doesn't want to be named, and helped them run far more experiments on an enterprise storage system that's currently on the market today. Allowed them to go up to run, millions of experiments when they were able to run 50 on their own before we started talking to them. And at the end of the day, their product shipped out the door with double-digit performance improvements in the caching that was in front of the storage. So we do have proven results on making this simulation work and being able to deliver high-performance parts out to the world. And I just wanted to, to sum this up, that, we're all storage geeks here, but caching is used for far more than just storage. That there are ways that we can improve content delivery networks very vastly by just doing some experimentation on them rather than going out and building the POPs ourselves. And that these simulations are suitable for optimizing all sorts of different configurations. And it's not just performance optimization, it could be cost optimization, could be power optimization. If you have some other factor that you want to optimize on, we can certainly optimize on that as well. And that was what I was here to talk to you about today. Questions? Yes?
So when you're looking at the parameter space for simulation,
Yes.
Do you evaluate the weight of specific changes so that you can focus on things that appear to have more effect rather than things that are every time you change them, kind of nothing happens?
Yes. So the question is, when we're running all these various different parameters and configuration space, are we able to weight certain things to say this is more valuable or less valuable? And the answer is yes. And we can't run this and get 125,000 results and say, okay, here's what we're going to look at. The way that we actually run these simulations is we will run it with a handful of constraints and say, okay, these are the things that matter, these are the things that don't matter. We'll stop playing around with these things that don't matter and start playing around with new things to see what else we can do. So we do this, and in fact, I didn't talk about this a whole lot during this talk, but we lots of times, once we've come up with a reasonable set of variables that we want to play with, we will run a Bayesian optimization on it. So rather than doing an exhaustive search on it, we will start running tests and saying, this helps, this doesn't help, so let's start running more of this type of thing. So we end up doing those type of results as well. But yes, there are certainly things that can make a difference. And again, the cost factor, if you're fixed on cost, if you just want to say this is exactly my cost, then you can start optimizing on other things as well. But did that answer it? Okay. Any other questions? Okay, I don't even get heckled by Jay. Where's the fun in that? Oh, okay, there you are. Okay, well, thank you very much for your time, and please do rate this session. I'm interested to know what people's feedback is, and if I am presenting material that's useful to you, I would like to come back to SDC. So, thanks for your time.